Hello and welcome to 5 Minutes of Postgres. My name is Lucas and today we're going to talk about why Postgres updates are getting slower over time. This blog post by Laurenz from the Cybertech team talks about a customer situation that Laurenz ran into. This example has two tables. It has an item table and it has a sum table. The item table gets items inserted and then sum table continuously gets updated with the total as new items get inserted. This is done through use of a trigger. The sum table doesn't have any indexes, so we should be able to get hot updates. In this example, Laurenz script takes 60 seconds to load 10,000 rows, which is pretty slow. This is with the trigger that does the update statement. But if we drop the trigger, the script runs in less than 70 milliseconds. So clearly doing all these updates is a problem. How do we prove that updates are actually getting slow over time? Maybe the updates are always slow. Laurenz uses an extension called Autoexplain. I often like to use Autoexplain because it shows you exactly what occurred when a query was slow. If I rerun an update, it might be faster after the fact, but if I experience the slowness at a particular point in time, only Autoexplain can tell me what really went on at that time. Autoexplain gets enabled through shared period libraries. I can then set various settings to configure when it logs the execution plan. Each statement that's slower than log duration will be output to the Postgres logs, where we can then take a look at the performance and other details of the execution plan. Log duration 0 means every single statement gets output to your logs. This is a configuration that I would not use in production. Instead, what I usually recommend is turning log durations to something like 1,000 milliseconds, and then turning log timing off, which can have some overhead. What's interesting is, as we look at the first update, you can see that that's pretty fast. The first update takes 0.017 milliseconds. I have rarely seen statements that fast in production. The last update in the chain is actually much slower. If we compare these two times, you can see 0.017 milliseconds versus 1.6 milliseconds. So that's about 100 times slower for the last update. If you look at the statistics, everything looks pretty similar except the buffer statistics. It's counted as pages. Postgres was looking at 443 8 kilobyte pages. Note that the hit portion here means that this was actually in the shared buffer cache. So this wasn't necessarily slow from an I/O perspective, but it was slow in terms of looking at a lot of data. In Postgres, an update works by creating what's called a new row version and then marking the old row version as dead. In this particular example, the last update just had a lot more row versions to work with. Vacuum is supposed to clean this up. Usually you have auto vacuum running, and auto vacuum will remove these dead row versions produced by these statements. But the problem is that the copy statement is a single transaction, and vacuum can only remove row versions that are older than any currently active transaction. It's very important that you're trying to reduce long-running transactions to make sure vacuum can do its work and finish what it tries to do. Now, there is this notion of hot pruning. And what that means is when you have a hot update, hot meaning heap-only-tuple, so there are no indexes referencing it. Postgres can actually do a mini vacuum of sorts, where it just vacuums the page that you're modifying because it's already modifying that page anyway. And so this usually can dramatically improve the efficiencies of having a heavy update workload like this. However, that only works if you don't have transactions holding things open. In this particular case, because we have this long-running transaction, it doesn't actually work to clean up these dead row versions. At the end, Laurenz does show the pageinspect extension. Pageinspect is very useful if you want to prove what's going on. For example, here he inspects the very first page in this table, and he shows how all of the row versions are marked as dead in this particular page, but they also were marked as hot updated. You want to see successful hot updates, but because you had that long-running transaction, it wasn't able to keep up. The fix in this particular situation was using what's called statement trigger, which ultimately moves the update of this particular table out of the copy statement, and by that avoids having a long-running wrapping transaction around all this activity. In this particular case, that took the overall load to 90 milliseconds. Now, just a quick note, if you are seeing this in production, oftentimes this will lead to bloated tables, as we saw in this particular case. When you're running vacuum verbose, or you're running auto vacuum, you can see this notion of dead rows not yet removable. And this is really the main thing to look out for when your auto vacuum doesn't seem to be catching up and doesn't seem to be keeping your tables at the size you expect them to be. There's a couple of other cases, but really log-running transactions are the main cause that I've seen. Thank you so much for listening. This was 5 Minutes of Postgres. Subscribe to our YouTube channel to hear about next week's episode, and talk to you next week.